computer. Okay, right. So where do we stand with our lectures? Last time we've seen some distances, right? So we started with considering the space of possible probability distributions, which live on a simplex, and basically we've seen that there are two distances on this space: trace distance. Trace distance. Okay, I don't say. Let's try to write very small already from the beginning. It's not a good idea. Do you hear me well, by the way? Okay, trace distance, right, and fidelity. And we see that they both have some interpretation. At least for trace distance it was clear. For fidelity it will be clear a bit later. Okay? And then we've seen that for quantum states, so this is probability distributions, probabilities, and then we have like kind of the quantum states. Quantum states, I will just draw like kind of the analog of a block sphere, and so it doesn't really have an analog in this simple sense, in larger dimension. But yes, just here we had these distances between probability distributions, which had different meanings. Then we also see that there is a trace distance equivalent, which can be defined directly on density matrix, right? And we've seen some nice properties that it actually corresponds to the best case trace distance if you do a measurement on the two states, and some other stuff. And then you probably use it in the exercise. Wait, I close the window because there's some noise. Did you manage to solve the exercise, by the way? Some of you? No, I don't. I'm sure I can hear you.
Partially. So.
Yeah, the first ones were not that hard, but the last one in particular, finding the POVM, that was confusing for me in particular.
Yeah, I realized I should have sent you the lecture notes because I had them already. I mean, there was lots of time. Yeah. Because it's not easy to just read from the video, I guess, or if you took notes. Yeah. Anyway, well, you've seen that it's useful, right? Because in this exercise, we've seen that this trace distance really allows you to see how to optimally measure in some really like kind of real life scenario, how to estimate if there is a magnetic field or not, right? In a single run. So yeah, just today we are going to finish this. So what's missing here, right, is the fidelity, the quantum fidelity. There is actually a quantum analog of fidelity as well, right? So we'll do this, and we'll see then we'll see relations with trace distance, and also some properties. Okay. But turns out it's a bit more involved than for trace distance in the quantum case. So I'll need first to remind you some linear algebra results, which anyway is good because, well, finite dimensional quantum physics, right? So on finite dimensional Hilbert spaces, basically, since we present everything in these complex matrices, really you can apply many things in a very nice way. So we'll start by just some reminder. So let me put it like this: one reminder of some linear algebra. I'm not sure, maybe you've seen it last semester, some of it, maybe not, but of some linear algebra. It's anyway, we're always good to repeat things, I think, especially if they're not trivial, right? Yes, so what first thing, which you know, and we use it many times, but it's still good to write it. So let's have an Hermitian matrix. So H is an Hermitian matrix or an Hermitian operator, right? So a matrix is an operator if you fix the basis. It's a representation of an operator. So Hermitian operator, so Hermitian, well, we know this all. So Hermitian H is such that it's equal to the adjoint, okay? Then for the matrix, it just means that it's invariant under transpose conjugate. And basically the nice result which we use all the time is that an Hermitian matrix, Hermitian H can be diagonalized in any basis. So not in any, okay. So it means that it can be diagonalized. In other words, in any basis, I can write H as some unitary matrix, then some diagonal matrix, right? And then the conjugates, okay? So you all know it, of course. And the U is just a matrix. So basically, U here is a unitary matrix. So unitary matrix, if you remember, is just the one which corresponds to a basis change. So it's like a rotation in real spaces, in real vector spaces, right? it's the same. It's just a basis change. So basis change, then some diagonal thing. So just shrink the vector, then go back to the previous basis. That's what it does. Right? Very nice. But not all matrices are diagonal, so are diagonalizable, or Hermitian. Even less. So next thing we will see is a single. Next thing we'll see is a single value decomposition. Do you remember this? Anyone? Singular value decomposition? Well, okay. So now we'll just forget the Hermitian matrices. Now we have any matrix, any operator. O can be put in a form. So again, for any basis, we can find a form like this. So O is equal to some unitary matrix, then some positive diagonal matrix, and then some other unitary matrix. Okay, so this is a unitary, this as well. Now this holds for all possible matrices. The difference is that you see that there are just with this freedom you can really fix all these eigenvalues here or singular values I call to be positive. Whereas in the case of diagonalization, you really cannot change the sign here because you have much more constraint. Okay, so any matrix or operator can be put in this form. And then of course, so since this is diagonal, the eigenvalues. So the eigenvalues are sometimes, so this D. Sometimes I call like singular values of, or actually they're always called singular values of the operator for the matrix. Okay. Yes, so this diagonal things here, they are singular values of the operator. Okay, nice. Now with this thing, we can define an operand on the operators, which is the absolute value. So we can define the absolute value operator, right? So let's take now another. Let's take our operator O, which is not necessarily a Hermitian, an operator or a matrix, and we will define just the absolute value operator to be the following thing. Okay. So it's just we take O multiplied by the adjoint and we take a square root. Okay. Now what does it mean to take a square root? Well, why can't we take a square root? Because of course, actually we used something like this, like the absolute value operator. We used it already last lecture without asking, but there we use it for a density matrix, or actually a difference of density matrices. So for an Hermitian operator. For an Hermitian operator, it's kind of, I mean, I guess you remember this, it's kind of easy. You just, any function is just, any function in the diagonal, in the eigenbasis is just a function of the eigenbasis, right? And then you have these unitaries which just pump up, right? But now this is also defined for non-Hermitian operators. Why it works? Because of course you can check that this thing here, so O adjoint, this is Hermitian, right? So if you take an adjoint again, this will just be, well, double adjoint times O adjoint. So this is just O. Okay, so since this inside the square root we have something Hermitian, well then we can take a square root. Okay, so we can take a square root, and in particular if you use use a single value decomposition. Use a singular value decomposition. Then we see that, so remember the singular value decomposition was something like writing O as U diagonal positive and some other unitary, typically with a dagger. So this will become, well, U, this D, 0, then we have D dagger here, then we have the conjugate, so V, U dagger, okay? And we can take the square root of this because, as you can see, well, this gives identity, right? So we can erase this guy here. So what we get here is U, well, yes. So we get something positive. This is a positive operator under the square root, so we can take the square root, right? So the square root will be just U, D, U dagger, okay? If you use a single value decomposition here. So it's nice because, well, for example, sometimes you're interested about the single values and the sum of the single values, which is a trace of the absolute value operator, right? Okay, this is something, and now we're using this, so we have now seen the single value decomposition, the absolute value, and now we can also define the polar decomposition. Okay. polar decomposition of a matrix. It will always we'll use it later, so that's why I'm actually bothering with this today and probably also later in the lecture. Also, it's kind of nice to know. It's kind of useful sometimes. So now we have the polar decomposition. The polar decomposition of O is just we can write it like this as an absolute value O times some unitary here. This is just Hermitian positive operator or non-negative actually, and this is unitary. Right? Did you see this polar decomposition anywhere before?
No, I haven't seen it.
Okay.
No.
Yeah, so again, we can just it's all derived kind of from the single value decomposition, because if you plug in the single value decomposition of this, then remember we have this thing. So this O here, right? O. So we had just on the previous whiteboard, we just seen that the absolute value O is just basically given by U, this D, the singular value matrix U dagger, and O is U D V dagger. So the another unitary. So we can just obviously see that here, if you just expand this line, so we get something like what I get? U D check V dagger, right? So we can multiply simply here. Okay, and we say that this is equal to U D 0 U dagger V. So this just means that these two guys are equal to this guy, right? So in other words, they have to be equal. This is the condition. So W is, if I multiply, so I have, okay, we have this equality now, which has to be fulfilled. Or in other words, W is equal to multiply by U on the left, so by this. Okay, obviously the product of two unitaries, it's a unitary as well. Okay, so we have all these nice decompositions. Right? Yeah, that's it for the composition of matrices. So just to remind you, a little box here. We have, so Hermitian matrix, well, this is kind of, you know it very well, right? And then another one which is not necessarily Hermitian, this is the singular value decomposition, and this is the polar decomposition. Okay, and the absolute value is, you also remember, right? Okay, let's just keep it here. Now, one last thing I want to show you before we continue is the Cauchy-Schwarz inequality, right? Do you know the Cauchy-Schwarz inequality?
Yeah.
Yeah. Yeah, it's a trivial inequality. Like in vector spaces, we all know it. It's kind of so intuitive. But of course, it also applies in Hilbert spaces. It's property of the inner product or scalar product. So Cauchy-Schwarz inequality. How do you write it? Schwarz, I think like this. Inequality. Okay, here what we is just so this is a property. So if we get two elements, I don't know, A and B. So these are elements of some vector space, like Hilbert space, for example. Actually, in Hilbert space or vector space in particular case. Then the scalar product or inner product is smaller or equal than this squared, then this one, right? So which this also is this is a norm of A squared, right? By definition of the norm. This is norm of B squared. So in vector spaces, it just means that yeah, if you have the scalar product of two vectors, obviously this cannot be bigger than the product of their lenses, right? Because it's just the product of lenses times the angle, kind of, or not the angle, but the cosinus angle. Right, but of course it also works for. So it's a very general thing. It works for whenever you have an inner product. It also works for states, right? So for example, this is true, of course. This is true trivially because they're normalized. Quantum states are normalized, right? So this would just be the norm of psi and the norm of there was a square. There should be a no. That's true, yeah, because now there's a square root in the norm with respect to this. So this is 1 and this is 1, okay? So basically we use it all the time to know that the overlap of two vectors is smaller than 1, right? Cauchy-Schwarz thing. However, there is another nice inner product and another nice Hilbert spaces, which we actually use it a couple of times, but I'm not sure you're aware of. This is a Hilbert-Schmidt product. Do you know what it is? No, you don't. But you know, it's when we basically, I'm sure we wrote it down somewhere in the exercise. Basically, when you use the orthogonality of Pauli matrices, right? They all are orthogonal on this trace, and actually this trace, the thing you write, is actually the Hilbert-Schmidt product. So Hilbert-Schmidt product. Check. The product. This is a product between two operators. So operators, right? They can be also expanded if you think of it like the density matrix. You can always expand it in some basis of operators. Like for a qubit, it would just be Pauli's. But in general, you can use other bases, like just put the 1 and zeros everywhere else in the matrix, right? Basically, just write it as a sum of coefficients. So it's another space. So for two operators, we have the Hilbert-Schmidt product is given by A and B then. Oops. So A and B. This is given by trace of A, B, dagger, right? So you probably remember, right? So it's familiar, right? Because when we have this Pauli relation, right? The Paulis, they are orthogonal, and this just means that the trace of sigma I, sigma j intermission is equal to delta ij. So Paulis actually are not orthogonal basis in the space of qubit operators, right? Hermitian operators. Well, if you use just complex phases, then we get algebraic complex coefficients. Okay, so this is the Hilbert-Schmidt product, which you all met already, but you maybe just didn't know the name. And the nice thing we will use, and this is the last thing I promised before we go to fidelity, is we just apply the Cauchy-Schwarz inequality to this inner product. Yes, basically, how do you see that it's an inner product? Well, well, obviously it's linear, right? So this is, you remember what you require from inner product, like linear, accessory linearity, so it's linear in this coefficient, it's linear under complex conjugation of a scalar in the second coefficient, so this is obviously true. And then it also has to be the case that it's only 0 for the 0 element, right? So this is for the norm, right? So basically, you can see that this thing, if this is 0, right, then this is trace of A dagger, and this, as we see, this is a trace of the absolute value of A squared. Okay, so the only, right, because we define the absolute value like this. So yeah, so if this is 0, then all the singular values here are 0. So this operator is also 0. Right? Good. So it's just to give you some hint why is it in your product. Yes, just take this relation and apply it here, and we get what we want. So basically, we get the trace of AB, right? This is of AB conjugate is smaller or equal than trace of AA dagger, trace of BB dagger with a square root. Okay? Are you still here? Or actually, if you see, of course, I can also use the inner product of B with another operator, which is just the adjoint, and then we'll get this. But for the matter, it doesn't, so I can just use the same relation with, so the trace is cyclic, so it's the same. Okay? So I just added here because this is, we'll use it later on. Let's just keep it in mind. So trace of AB is smaller or equal than square root of trace of AA dagger, trace of B dagger. Check. So this is a Cauchy-Schwarz inequality for our operator products. Good. So yeah, this was about this kind of reminder of tools we'll use. Do you have questions on this, or maybe some comments? I don't know.
So
No?
far, so good.
Say again?
So far, so good.
So good. Okay. So basically, all these things are derived from. Okay, we have the cosmetic ingredients. We have the single value decomposition and Cauchy-Schwarz inequality.
It's a bit hard to see because of the reflection in the whiteboard of your window.
Yeah, actually, I put some. Yes, so what to do? Think about it. Well, maybe I can write bigger. What do you think? Just let's try for 5 more minutes. I try to write bigger.
Yeah, it's only a small part. I think it works.
The problem is still there. We can do something more drastic, like close the stores. Okay. So try to write bigger. Yes. So now let's go to fidelity. So this was the reminder. So now I have the fidelity between quantum states. This is part 2. Fidelity. Yes, this is not clearly bigger. So this is fidelity between quantum states. Okay, so we have 2 states, sigma and rho, density matrices on some finite dimensional Hilbert space. And then I just give you the definition directly, and we'll discuss what it means afterward. So the fidelity, the quantum fidelity is between the 2 states is given by Mitter-Weir formula. It's a trace of the square root of the square root of well, it doesn't matter, that's symmetric. So okay. Looks weird, huh? This is the definition. So of course this is density matrix with a positive, so in the emission, so square root is a valid thing. Good. So let's see. So now what we want to do is basically we want to do the same story as for the trace distance. So to show that this corresponds, so first see some examples, and then show that this corresponds to the best case, actually the worst case fidelity. So the best case, but now the maximum fidelity for measurements, the minimal fidelity for among all possible measurements, right? And this proof is a bit lengthy, but first let's just to get some intuition, let's just see what it is for pure states. Okay, so first 2.1 is example. So we take the example of pure states. Pure states, and for pure states, it really becomes easy because we just have f of phi. So I've got 2 projectors. This is just so obviously you. 1D project, well, for any projector, the square root of a projector is also the same projector, right? Because it's just a matrix with 1 somewhere. So it's just a trace of, let me write it first, square root of psi, psi, phi, psi, psi, okay. And I can just erase square root 1 by 1. So just the square root of this projector is itself. So just remove it, okay. Now the square root of this projector is also itself. So we're just left with this overlap here, okay. So I'll just write it here, maybe. So this is equal to the trace of, you see we just have remaining this cat here and this bra, and this guy is just the complex number. So this is a complex number, this is a complex number. So we're just left with the trace of this thing times psi phi times phi psi. So times psi phi squared. Yes. This times the conjugate. And of course, again, this is a number. So the trace of a square root of a projector is again a projector. So basically, it's just this is just overlap. Psi phi. Okay. So f of psi. Okay. So it's for pure states, it's something very simple. This fidelity. It's something very well used too. It's the overlap of the states. Of course, now let's see what it means for mixed states. First thing I was actually now using, I think I was jungling around like the order of the thing, because this here, the order is important. No? We're going to have sigma kind of appearing here and rho in the middle. So first thing to show is that actually it's symmetric, right? As we would expect. And to do this, we will just, we can actually will rewrite it, because we can rewrite it in a nice, or maybe not nicer, but you see what this thing is? Basically, this thing here, inside the square root, right? This is just square root of sigma, square root of rho, times square root of rho, square root of sigma, okay? Or this is square root of rho, square root of sigma, and then the same thing, square root of sigma, square root of rho, dagger, right? This is all equal. So in other words, we have this absolute value operator showing up, right? So this means that the trace is, you see, so it's a square root. So trace is, so that is a trace of the square root of sigma, the product of sigma rho square root, and the product of sigma rho square root conjugate. So this is really the trace of the absolute value of sigma and rho. Okay. So let me just write it down here. So it's a trace of the absolute value of square root of sigma. Square root of rho. Now the point is that here we can exchange them. Now how do you see this? Oh, well, probably to see this we need what do we need? Yeah, okay, well, it's actually not difficult to see, yes. But we do need something. Okay, so just keep it in mind. So let's just continue. And to see this, we will need something else. Is that we take this thing here, right? So trace of this thing. So I'll just show the following thing: the trace of O, absolute value, is smaller or equal than trace of its the trace of this thing, right? Okay, of the absolute value. Then we'll use it later on. I think I forgot this relation. We'll have to use it. So this is just again to show it. We can use this Ilbert-Schmidt product because, because here we have this is trace of O W. Okay, for some W using the polar decomposition, absolute value, and of course this thing is just the trace of square root of O, square root of O W, okay. And now using the Ilbert-Schmidt thing here, so the Cauchy-Schwarz inequality, we see that this is smaller or equal than, yes, with this, the square root of, yeah, so we can also use it like this way, with absolute value squared without the square, which is the same thing. We need the absolute value for this. Well, not because inequality still holds without it. Okay, so we get trace of O. Check square root. Yes, trace of O. Another A. Trace of OW square root. And how do we show that this is the same thing? Let me check in the notes, because it's not. I have them here. Yeah, no, it's a bit lengthy today, but so there are many technical details. that you noticed probably, but next time it will be better. We'll just have, it's actually not easy to prove this first relation. So where it is, wait a second. So we're done with things. Right, so what we want to use here is this relation. So we have the trace of the thing, and this is the trace of this times the emission conjugate. So for this case, the W should be squared, yes. So let me see how I prove this. Well, yes. Oh, yeah. Sorry. This is actually obvious from here. Sorry for the confusion. So let's see what we get here. Yes. So this guy times the emission conjugate. So it's this times W dagger square root O square root, right? So obviously this is identity. So here we get just the square root of, so the square root of trace of O squared, okay, which is precisely trace of O. Yes, square root of trace of O squared. Okay, so it shows this relation. Actually, we want something a little bit. We want a little bit more to this, but it's the same story, and we want to show that it's actually also with any unitary. So if you plug it here, any unitary, this relation will still hold. Okay, but this follows exactly the same lines. We just get trace of square root of O. So right, this guy W unitary. So let's just define this as a new unitary. Okay, let's do it again. So this is what we want. This is what we have here. Again, decompose it as a square root times the square root. So this is trace of square root of O, square root of O times W U. Using the polar decomposition, now we use again the Hilbert-Schmidt product, which tells us that this trace is, so the product between these two operators, this one and this one, is more equal than their norms, or that the trace of O times the trace of times the trace of, what do we get here? VU, let's write it. Times the conjugate. No, but this is here. Wait a second. Sorry guys, I messed up with this here. Well, which is indeed, well, which is the same, right? Still, so this is still valid, this equation, right? So we also prove this thing here, right? For any O on the left hand side. Good. Are you still with me, or?
Yeah. Yes.
Yeah. Sorry, this was a bit messy. I know. Finally, let's now go to what we want. So we have these things. We just proved this trace of O times NU is smaller or equal than trace of the absolute value operator. Now we are finally ready to attack this thing that the fidelity is. So what we want to show is that the fidelity of operator between quantum states, which we just shown, right, is actually equal to the best case. So fidelity, now remember, it's like the opposite of the distance. So if the states are far away, the fidelity is small. So this should be kind of the minimum. So the further away the states are, minimum fidelity between Now probability distributions, so P and Q, where P and Q are precisely given by some P of M Ek, where each Pk is equal to trace of Ek rho, and each Qk is equal to trace of Ek sigma, right? So in other words, this is just some abstract relation for the moment between operators which you've seen, but this is very clear what this thing is. It just means that we take the two states, we measure them with this P of M, so with this measurement, we observe some outcome with some probabilities, and then we define the fidelity between this outcome probability distributions. So this is something which is operational. We can get this fidelity by measuring. So if we prove that this is indeed the best case, then again, like for the trace distance, we can just forget about this optimal measurement now, or at least just keep it in the back of our heads, but just use this thing as directly the measure of this distinguishability between the two states, given by this fidelity. Okay, so how to do this? Well, now, so first thing we'll do again is same story as before. We'll just show that this is always larger, smaller for every P of M. And to do this, we just, so first step is just show that this is smaller. So let's just look at what this thing is. Yes, so rho and sigma. Okay. This is equal to, as we just seen, another formulation is that this is a trace of this thing. I don't remember the order, but it doesn't matter. We just change it. Argument at the end. Because here the order doesn't matter, right? Okay. So this is a definition, one of the definitions we've seen it's equivalent. Now this thing is smaller or equal than trace of sigma rho with some unitary. Okay. Actually, no. Let's do something else. Let's take because we have this W here, right? So we know that this operator now is given by this thing times some W. Because there exists, we just pick the W from polar decomposition. Polar decomposition. Yes. So it's clear now. We take this thing, so it will be W dagger actually, because this thing is equal to this times W here. So we just pass the W on the other side, so these two operators are equal. Then the traces are equal. Okay. Yes, and now what we do is we just insert identity. So we assert identity here. We say, okay, well, but then this is just equal to the sum over K of trace of. Well, I'll not erase it because we need some space. I guess it was enough already, so you could remember it. It was enough on the screen, maybe, so you can remember it. Probably not. Okay, Ek square root of rho W. So we just inserted here the sum of P of M elements, which is identity. And we can also just decompose this P of M element. They're positive, so check, take the square roots. Yeah, well, now what do we use now with this? Any idea? We use it all the time for the past 20 minutes. Just again, the Cauchy-Schwarz inequality, right? So we take this one and this one. So let me rewrite it again. So we see that fidelity of rho and sigma. This is basically equal for any choice of P of M. It's equal to sum of K trace of square root of sigma Ek square root of Ek rho W. Okay, and now using the Cauchy-Schwarz inequality, this is just the scalar product between these two operators. So it's again smaller or equal than the norms. In other words, smaller or equal than the square root of sum of K square root of 4 trace of let me just write explicitly Ek so that I don't get lost again. Right, the absolute value operator. So this is the norm. And here we get the same story. It's just Ek rho W times the emission conjugate Ek square root of rho W. Okay, and the big square root is over everything. Well, now just open these things. So we get here trace of square root of EK, right? This guy. And here we get trace of square root of the POM element, rho W dagger W, square root of rho. Okay, so you see where we're going with this, no? I guess, because this thing is, this is just, well, this is trace of EK sigma, and this is trace of EK rho, sum over K, sum over K. Precisely, this is precisely the probability. So this is precisely sum of K of PK, sorry, QK here, then what does it mean? PK, okay, which is the fidelity of this probability distributions obtained so by the POM we choose. So this holds for any POM, right? We just inserted any kind of identity partition here. All right? So any POM we can insert it. So now we show that, so what we show here is this story. Wait for it, this is actually important line. Sum of K, but this probably we can erase. No, oh, let's erase here. So we show that it's always true that the quantum fidelity is a lower bound on the classical fidelity for any choice of POM. Right, similar as we did for trade distance. Now what remains to show is that there is a choice which attains it. Somebody, there is a chat question. Right? And once we do it, we can, so next step is really the crucial one. Once we do it, we can then take a break. Fine with this, so let's now show that there is indeed a POM which attains this. Like we did, it's sort of the same idea of the proof we did for the trade distance, right? We were doing exactly the same, showing inequality and then finding this POM. Now the only difference that's here, the POM is a bit more tricky. And to see the POM, well, if you look on the thing, you see this is an inequality, right? But what we want, it will be attained only if, for each K, so this here is an equality, if and only if, for each K, actually, each term is equal. And each term is equal if we get trace of square root of rho EK times, so let me just write it now as a scalar product, as an enrichment scalar product. These two operators, W dagger, this thing is equal to, yes, to kind of the norm of these operators. Sigma EK norm times norm of this operator. The norm which is induced by, so this is precisely this thing here, by the scalar product, well, as usual. All right. Okay. Now, when can it happen when this thing is equal? Well, it can happen only if they are proportional. So the norm, right? It's like now remember just a normal vector. So what do we have here? We have two vectors, and we say the scalar product should be between the two vectors should be equal to the product of their norms, which means that they are proportional, right? Do you agree with this?
Yes.
Yes. So it's the same thing here. So in other words, this equality can only be satisfied. I mean, you can just really map it to kind of your vector representation, because you can expand all these operators in some operator basis with this Hilbert-Schmidt orthonormal basis, like the Pauli, for example. That will really just be vectors with complex coefficients, and they have to be, their absolute value has to be equal to, yes, so the scalar product, the product of the vectors has to be equal to the product of the norms. So in other words, this is equivalent to having that they're actually proportional. So meaning that this thing sigma EK has to be equal to some number here, alpha. Well, let's put alpha K times square root of EK times other one. Yes. Right. Okay, good. So what does it mean now? And now we can just assume for the moment that because it's simple. We just assume that this is this matrix here is invertible. So we assume that this matrix is invertible. Then forget this, and then we will just list the assumptions. So first, assume that assume that sigma is invertible, and this just means that there is no, it doesn't have zero eigenvalues, right? We'll just treat the other case directly afterwards. So assume that sigma is invertible, then we can just equivalently apply the inverse of sigma here, and we just get ek is equal to sigma minus 1/2. So this is alpha k here, square root of ek rho, there is a square root here as well, sorry, rho and w, dagger. Okay. On the other hand, if you remember, we also had something like square root, wait, square root of rho, square root of sigma. Remember this? We said that this is equal to w, dagger, right? Or was it the other way around? And this is equal to square root of rho, square root of rho, square root, which we also have shown. Okay. So just to summarize this. So we have the square root of sigma, rho square root of sigma is equal to this. Okay. So now we can also get the expression of this guy, but I think I missed. Yeah, because we can also multiply by rho here, right? We can multiply by rho here on the other side, and then we get rho minus 1/2. Okay, and then we could plug it in. Oh yeah, sorry, this is of course square root. Then we can take this and plug it in now probably here. And with this we'll get something like well, actually I don't like it so much. You know what, maybe I suggest I think I messed the order of the operators at some point. Maybe take the break now and then I'll just have the time to fix it. Do you mind?
Okay.
Okay. Because this guy, I think it should be the dagger here. Then it will work, but not like this. So yeah, sorry for this. It's a bit lengthy. So I'll just take 10 minutes break or now and then start on the same point.